Okay, it's 10:40. Welcome. My name's Steve Rostedt. This is the title slide that LCA has told me to do, but since VMware paid for me to come here, I have to do this to let everyone know that, yes, I work for VMware. And you might say, well, why I'm working for VMware? But they're trying to become kind of a directive from the CEO, like they want to be more involved with the open source community. So I was hired, I was 10 years at Red Hat, came over here. My job is to be an open source advocate, both outside and towards inside the company itself. So I'm actually pushing open source procedures within the company. And also I'm to come out and still be paid basically full time to work on open source projects. And because of VMware, I'm able to do this presentation, and I'm happy for the support they've given in the support of my work. So anyway, this is a tutorial, and before I go, I have my own little thing. I do selfies, but you have to understand, I've been doing selfies since 1984. My first selfie with one of those yellow disposable cameras I used to crank for those. There's a lot of people like around my age. You guys remember those. And I was in Hawaii, and I kept taking pictures of myself. And my dad was like, "You can't take pictures like that because your arm's not long enough." Blah blah blah. Those are my best pictures I took. So ever since then, I always use a selfie with a real selfie camera. I bought a new one here. So smile, everyone. Let's see how I get everyone there. Yeah, this one has to hit, well, I have to hit play. Yeah, that's good. I'll post it on my Twitter account. So anyway, like I said, this is a tutorial. So I've given this talk a few times, but I never really had it where I really want you guys to try to play along. Ideally, you don't have to. You could just sit back and watch. But if you can, to get the most of this, if you can open up a root shell. I know if you don't want to do that, you can do sudo on everything, but I like screw it, just do root because Ftrace. Let me ask, who here has not heard of Ftrace? Okay, a few people. Wow, it's quite a bit. Good. It's the official tracer of the Linux kernel. Allows you to see events that are happening within the black box of the kernel. You can have, I'm hoping those that said they'd never heard of Ftrace. How many have heard of Strace? Yes, okay. Strace is the thing that you see the system calls, which is a communication between the application and the kernel. But before Ftrace, you were not able to see what the kernel was actually doing. Every so often you might get a print K, they could look at dmessage and see what happened, but Ftrace was actually made to see what actually happened inside the kernel. It came from the real-time patch. The real-time patch is something that we really had to analyze the systems because we're trying to find latencies, and the real-time patch is about determinism, and we had to be able to make the system completely preemptible, and whenever we had a long latency, we had to find out exactly why. So what we did was we did a lot of tracing utilities and this, and people were asking, why can't you bring this to the mainline kernel? I rewrote the latency tracer. I had my own little tracer, and I put them all together, and this became Ftrace, and then suddenly, boom, it became a whole beast of itself. And instead of being a real-time maintainer, I became the Ftrace maintainer. So anyway, if you can, I've already mentioned, this is the link on my USB disk. If you want, yes, you have a question, or you want to pass it? No, are we supposed to do the make GUI if you can as well. Compile the GUI. The question was, can you compile the GUI on this? Compile the GUI. For those watching this that are not here, this get clone of my USB disk won't be very helpful to you. So for those that are watching this either on YouTube or live streaming, or both, you would want to go to get.kernel.org, search for my last name. You'll find that /trace-cmd.git. Go to that thing, download the code there. It just basically install GUI. You might need some dependencies within the kernel-shark directory. There'll be a README file. Look at the README file. It'll tell you what dependencies you would need to build the GUI. And you can do that now while you're doing this. So where do we find Ftrace? Well, Ftrace is basically on every computer here that's running Linux. It's even on your phone, believe it or not. Android actually uses it. I have friends in the Google community that tell me that they use Ftrace all the time. And when you root your phone, you actually can do everything I'm doing right now. I'll show you on your phone if you have it rooted. It's going to be, most distributions mount the debug.fs directory, which will be in sys/kernel/debug. You can also, if you don't want the debug.fs, you don't have to compile the debug.fs directory, because that also adds a lot of debug code, which can make your system vulnerable. So if you just want tracing, you could go to sys/kernel/tracing, and you can mount the trace-fs directory, and this is the command you would do. So if you want to do that, or, okay, so let me see. How many people are kind of following along here? Okay, how many people are now with a root terminal open? Okay, can you see or do ls-/sys/kernel/tracing? Is there anything in that directory? No. Okay, do that command, or oops, wrong button. Do that command, that one. Mount-t trace-fs space no dev sys kernel tracing. It's probably in this directory already. There's going to be a debug/tracing directory. Don't use that one. I want people to learn how to mount a directory, mount the directory. So this is a tutorial you should learn. So mount-t trace-fs no dev /sys/kernel/tracing. Got it? Still nothing. Oh, you got to be root. You are root. Oh, you got like SE Linux or something going on there. Oh, really? Or what is that, a Mac? No. Okay, unfortunately, you might have to go look at someone else, because I can't play. I don't have time to debug things. Maybe I'll come with you later. After this, you'll get a free tutorial by yourself if you have time for lunch. Okay, if you want, because I really want people to be able to do this. So if you have questions, please stop. But if you look in the directory, this is what you see, something kind of daunting. There'll be a lot of files. I highlighted some of the files that we will be talking about within this tutorial. But right now, I got to move on. You'll see a README file. Greg Kroll-Hartman was actually quite shocked and pleased that he once went in and goes, wow, the tracing directory has a README. And it's actually quite informative. When we first created this, the very first thing that the README told you was how to mount the trace-fs, or actually it was debug.fs file system, which was kind of like a catch-22. You can't see the README unless you mounted it. So when you mounted it, you learned how to mount it. So, but the one thing we actually try to do is we actually use the README file to let you know what features are enabled, because Ftrace has a lot of features that are config specific. Some things you don't want to run on a production system, so you would have it enabled on your debug system. So to know what's enabled and disabled, a lot of times we try to make it so we could just look at the README file and figure out, okay, this is what's enabled and what's not. And there's other ways to find out what things are enabled. If you look at, there's a file called available tracers, cat it, see what you got. You'll see various things. You'll always have the no-op tracer. The tracer is kind of like special commands that you could do or make the tracing system do. The no-op tracer just basically is a tracer saying, I don't want you to do anything, or just put you back to default. That's the default tracer. The function tracer, which is just function, don't enable that yet. You could if you want. If you enable the function tracer, you will trace every single function within the Linux kernel. Function graph tracer makes it pretty. The block BLK, I'm not going to talk about this. It's how the block trace works. That's a completely different maintainer for that. So I'm not going to talk about that. I do want to talk a little bit about the MMIO trace. How many people? Okay, how many people are kernel developers here? Just curious. Two, couple. Okay. Embedded developers, or how about people that will likes to reverse engineer binary modules? Got one. Are you familiar with the MMIO tracer? You're not familiar with the MMIO tracer. Okay, I'm glad you're here. I didn't create the MMIO tracer. Someone else created it, and I thought this was awesome. If you enable the MMIO tracer, first of all, it will put your system into a uniprocessor system. It will shut down all CPUs but one. And the reason why is because all the code that this does, the guy didn't. It was already so complex, he didn't want it to worry about SMP. So when you enable it, you just like turn off all the CPUs. We're a uniprocessor, no SMP. I don't have to worry about locking or anything else, or synchronization or races. No races. What it does is this. If you're familiar with how a device is, when you plug in a device or whatever, it'll usually, the way a driver will talk to that device is it'll take a part of it, or map part of the address space to the actual device memory. So you can actually control the device, the NVRAM or whatever, through this magical address space, and by reading and writing to it. What the MMIO tracer does is it makes that magical space disappear. So when the driver goes to read or write from it, it causes it to fault. It takes a page fault. the page file exception handler, MMIO-trace, injects into the page file handler, looks at what that driver's writing or reading, does the work for the driver, records it in the buffer, what it did, and tells the driver everything was OK, go continue. So you get this nice trace of all the interactions between the driver and the hardware. Will that be useful? So that's all I know about the MIO tracer. I just know it exists. I don't. If you find bugs, I think there's another maintainer for it, but I think it's a cool thing. So that's why I always bring it up. Other available tracers that might be, like in Fedora has some of these enabled. Debian didn't. I'm using a Debian box right now. And that's the HWLAT tracer, which basically it will just put your system into a spin with interrupts off, and it's searching for SMIs, where basically the BIOS will take over the machine, and it might do something for a long time. Reason why we do this is for if you're doing real-time processing, you want to, if the BIOS is hijacking the computer, the kernel has no idea about it. So you can have these huge latencies and not know why, but it could be because your laptop has decided to, lower the fan system down or clean the memory. We have all things that the BIOS does, and some of those things could take a long time. I mean, like a millisecond. So hardware latency detector, HWLAT, is a way that it'll tell you when it finds latencies. We also have a wake-up latency tracer that you could enable that traces from the time a process were to go to sleep, when a process was woken to the time it actually schedules in, and it traces everything that happens in between. The wake up always tries to do only the highest priority task, but if you only care about real-time tasks, you would do the wake up --RT. If you worry about deadline scheduling tasks, sched deadline, don't worry about it if you don't know it. I've given talks on that. It only does those tasks. IRQ's off, you get to trace how long interrupts were disabled and find out where inside the kernel interrupts were disabled, which means that you can't do anything. The preempt off is when preemption is disabled. Doesn't care. But I always use preempt IRQs off because that's both preemption or IRQs. I worry about scheduling. And if interrupts are off, preemption's disabled by default, but that's not what the preempt off records. But preempt IRQs off records both. We won't talk about these, but they're good to know. Current tracer. Now, OK, let's start the function tracer, just so you get the idea. You could do it, and then just to see if it works. So all you do is bash command, echo function into current tracer. Very simple. Turn it off, echo no op, current tracer. How many people had their laptop hang? No one. No one had your laptop hang. Good, it works. What was that? Pregnant pause. Yeah, it will pause. Yeah, that's fine. As long as it comes back to life, it's good. Then go back to no op, ain't good. We'll talk more about that later. But actually, let's talk about it now. I did these slides like last week, most of them, and then I kind of finished up at the end later on. So actually, I forgot. I haven't looked at my slides again, so this is kind of a surprise to me as I go. So if you echo function there, and you did cat trace, let's do that now. Echo function, cat trace, see what you get. You see all these functions. I'll use my mouse because I think it's, yes. Those are the functions that are happening on your computer right now. So you can see it's quite daunting. Again, remember to turn it off because tracing functions can add to overhead, run benchmarks, and then and then enable function tracing and run benchmarks. It's funny is you can actually enable several functions. I mean, I've enabled over 100 functions tracing, and my benchmarks don't even show it. It's in the noise. So it's actually very, very fast. Usually a function trace happens, I think I'm down to about 200 nanoseconds per trace or something like that, or maybe a little less than that. Tracing on is a file that you'll see there. All it is an on-off switch, whether or not it's basically make the ring buffer writable or not. If you echo 0 into the tracing on, so you could type echo function, and then you type tracing on equal. Or let's do this. Enable function tracer. Okay. Echo 0 to tracing on. And if you cat trace and cat trace, you'll see it never updates. Everyone got that? I know I'm going to be going kind of fast, but I have a lot of, I have basically I have 120 slides or something like that. That's OK, we're already on 12. I've been told I speak kind of fast. So if everyone sees that tracing on, so I just want to show that tracing on stops recording. What's not in this tutorial, and I'll tell you right now, you'll see another file called trace pipe. That's actually, okay, the trace file, when you read it, it actually pauses, it stops the recording while it reads it because it's an iterator, but it's not a consumer. You could see it over and over and over again. There's a trace_pipe file. You read that, that's a consumer. So if you were to do tracing on or echo 0 into tracing on, then cat trace pipe and let it run because it might take a long time. It's like 1.4 megabytes per CPU you have. That's how big the buffer is. And only, by the way, it's pre-allocated. It's when you boot up your system, it's down to like only a couple K. But once you use the tracer, it allocates all that memory for you. So now you're wasting your memory as well. So if you hit echo 0, then do trace pipe, and then cat again, you'll see the buffer's empty. So that's how they kill it. By the way, if you want to erase if you do tracing on equals 0, I'll give you another. I don't know if I mentioned this in my talk, but I'll tell you right now. Just writing into the trace file, it's probably in the next thing, writing into the trace file will clear it. But I think I'll talk about that later. Caution. Make sure you have a space between the 0 and the 1 when you do tracing, when you echo stuff, and don't do forget the space. Okay, quiz. Who knows why? Redirection. Yes, you just redirected standard input and output into the thing. So I've had people actually complain. I actually had someone that was a very experienced kernel developer saying, it's not working. And I go there, put a space. And they're like, oh, yeah, crap. So yeah, it's a common mistake, so I always have to tell people that. Trace marker is kind of cool. Because, like I said, this is all the tracing is done within the kernel. Well, let's say you're doing something in the user space and you want to synchronize what something happened in user space into trace marker, or in the ring buffer. So do this, echo no op into current tracer, which will turn off the function tracer and clear the buffer. Make sure your tracing on's on. Echo 1, tracing on. By the way, I will upload. These slides will be available, so you can download it. Now, echo something into trace marker. Echo hello world or whatever you want. And cat trace. You should see whatever you wrote is now in the trace buffer. Everyone got that? Everyone ready? Okay, cool. If you're writing C code or something like that, I have several C code that I add this. Don't worry about it right now. Like I said, it'll be in the slides, or I'm going to have this is in the slides. But basic idea is I'll have like a setup trace marker, and I will make this global variable called like marker FD, and I'll set it to -1, and then I'll just in the beginning of the function, I'll open it and have a file descriptor for it. Then I have this other function that's like write trace marker, which basically checks to see if the marker trace marker is less than 0. So I have to be root or something to do this, because if it fails, if it fails, I don't want any error messages. I just I just don't trace. So all the trace markers will see markers like it failed, so just ignore the function. But other than that, it'll actually write into the ring buffer. So like cyclic tests, which is one of the utilities we use in the real-time kernel to see how much jitter the wake-up latencies everything has, it actually writes into the ring buffer with this. When it finds a failure, actually it'll write into the ring buffer saying, we found a failure here, so at least we could find that within the trace and then go back to see why it was delayed. So function tracing is great. You get to see all the tracers. If you see you'll see a file in there called available filter functions. That shows you all the available. Yes.
For that one, this is nice for correlation the user and the trace you want to measure, right? Can you do the same thing that you can, whether you can, and anytime you write C program to stop the tracing?
Oh yes. Okay. The question is, can you do the same thing for stop tracing? Actually, in those same files, in fact, actually in the cyclic test, I have the exact same thing, except it says tracing on FD. So I do the exact. I actually open. I should have put that in the slide. I actually do an open of a tracing. I don't just open trace marker. I also open the tracing on file. And the first thing I do, is I write the trace marker. The second I do is I write 0. I echo, or I do the ASCII 0. You have to make sure it's ASCII 0. Don't write the binary 0, but write ASCII 0 into that, and tracing stops too. So I don't lose the data.
Right. You capture what happened.
Right, and then I just extract the error. Yes, to say that's a good point. So basically, the idea is don't just do tracing on. Download, it's in the RT tests. It's, I think, on kernel.org. I think we also have RT tests or something that has cyclic tests in it, and it actually has code that does some of this. So function tracing, all the functions you could trace are in the available filter functions. And this means that you could enable and disable, if you only want to trace one function or 10 functions or 100 functions, all you have to do is write into the set ftrace filter. And there's also a set ftrace no trace, which is basically don't trace these functions. Hello. Someone's just sent me a message, which is probably why I shouldn't have here. Sure. Are you not? There we go. OK, so anyway, going back to this, I just want to make sure. It might be later in the talk because I forgot about it. For what the set ftrace no trace will do, sometimes I'll enable all functions, but there'll be a lot of functions I don't want to trace that happen a lot, like locking, spin locks, which will get traced. And I don't want to trace spin locks because that just adds to the overhead. So I start throwing in a bunch of stuff I don't want to trace, like spin locks, RCU code, something like that, stuff that I'm not interested in. I'll throw into no trace, but I want everything else traced. And it'd be a lot easier to pick functions not to trace than to pick every function and filter out what you don't want to trace too. So you can do that. The way you enter, you would echo the function name into, just like normal bash command, echo foo into set ftrace. If you want to add two functions, you just put a space or white space between it. So in fact, you can actually cat available filter functions into it, but you got to be careful. It does have the module name. You got to cut that off, otherwise you'll get an error. So I usually use a cut command. But anyway, if you want to add, say if you have functions in the set ftrace filter or set ftrace no trace, you want to add to it, you just do the concatenation of the greater than. And so just the normal bash command, how you get add and remove files. So, and it takes wildcards. So yes, we wrote a wildcard parser within the kernel. That was interesting. Anyway, like for here, I just want to echo this into set ftrace filter. You can write that command if you want to see what you get. So echo quote, question mark, lock star D, end quote, greater than set ftrace filter just to see what you get. And here, like I told you, you can actually use grep. If you want to use something super special, you could grep. And this is where I said use cut command. So I use the cut command to chop off the module names of the functions. So I only have function names. And then I grep for, like, say, I want everything that has IPv4.6 in their name. And I pipe that, or I redirect that into set ftrace filter. Yes, there's a question back there.
So is this only showing export symbols, or it's actually symbols that are internal to
The question was it showing just export symbols, or is this showing symbols internal to modules, everything? It's everything in k-all-syms. So it's every function that's in k-all-syms, which is basically every single function. Yes?
So what happens if two functions have the same function?
Function name, you'll enable both. The question is, what happens if two functions have the same function name? You enable both of them. Now, what's actually kind of interesting is, and I didn't put it in here. I don't know if I have. Maybe I did something special. You can actually, there's a special commands on here, and you could read it because there's actually documentation in the kernel source code that you could read. That it's in the documentation /trace/ there's a bunch of files there. And one of the little tricks you could do is like echo :mod : module name into this. It'll enable everything just for that module. Even if it doesn't care about names, just everything for that module enable. And you actually could do that before you load the module. And when the module gets loaded, then it'll apply it then. So you can actually trace it on module load. That's actually recently done. That's a recent kernel, like 4.15 maybe. Like I said, here's the cut command. So I did lock set ftrace filter. I did echo clock because I don't want to trace clock functions because lock, saying I want all lock functions, I get all the clock functions with it just because lock is within clock. So I said lock and then put clock into no trace so I didn't have to filter out anything. And then I got everything I traced. You could write that if you want. It's no big deal. We'll move on because it's got a lot to go. Function graph tracing. This is actually something that's really, really cool. It's like function graph tracing, but prettier. Not only does it trace the entry of a function, it traces the exit of the function. And this way allows you to see how functions, who calls what, and it gives you a nice, pretty display. And the way we do this is kind of what we do is when the way it's implemented, just to let quick it's kind of cool. So when a function gets entered, it traces it, will trace it normally like the function tracer does. But then it looks at the return value, or looks at in the stack, the return address. Or if it's a link register or whatever it does, it hijacks that, it takes it out, and puts in a new address for the return code that jumps to a trampoline. So when the function runs, when it returns and it pops off the stack, the return address where it's supposed to go, it doesn't go there. It goes to our magical trampoline that does a recording of the exit, and it saved the where it's supposed to go, puts that back on, and then jumps directly back. So there's a lot of, put it this way, tracing makes the security folks pull their hair out. This is what function graph tracing looks like. So you do it now. Echo function graph into current tracer and look at it. You'll see it much prettier and easier to read. Be warned, although function graph tracer is going through a rewrite right now. I'm rewriting the code because we're going to try to make it faster, a little bit quicker, and also more flexible to allow multiple multiple subsystems to be able to reuse the function graph tracer. Function graph tracer slows your system down by like, X amount. Well, function graph tracer will slow your system time down by 4x that amount. So it's a much higher overhead, although I think we've fixed it. We've gotten it better on x86. It's actually much the best, but it used to be PowerPC until my PowerPC machine died, so I can't support PowerPC anymore. And I have a bunch of ARM boards, but I never got around to it, and other people know ARM much better than I do, so I let them maintain that. So I usually do all the work in x86, but I would love it to work in other architectures as well, and I'll work with the other architecture maintainers to help them implement the best features to make things more faster. Here you'll see the timestamps, which shows you not only that, it records the timestamp when it enters, and it uses that timestamp to figure out, okay, how long did that function take? Be warned, because of the overhead of function graph tracer, when you enable the function graph tracer, if you're looking at like down here, you'll notice this thing. There we go. Does that show the mouse? Yep. If you hear, there's several other functions that was called. All these guys were called. These hold the overhead of these guys. So this is an exaggerated version. But where you see a single function, you'll see a semicolon. It actually traces both sides, but the tracer will know that, oh, there's nothing in between these. So why put a little bracket? We just make it look like a normal function. This is actually very, very accurate, because it only has part of the overhead, and the overhead's still much less than a microsecond, still in the nanoseconds. So this is usually about, and this is like what? Like I said, it's telling you that this function took 0.045 nanoseconds, basically 45 nanoseconds. So that's basically part of the overhead. That's probably mostly the overhead of the function graph tracer. This is where I talk about don't trust the times and all that. Basically, this is everything I just said. So I'm going to kind of jump over it. Oh, except for the last bullet point. The set ftrace filter and the set ftrace no trace affect the function graph tracer as well. So basically, again, if you only want to trace one function, all you have to do is use the function graph tracer or the set ftrace no trace or the set ftrace filter, and it will only trace that one function. So what I like to do is this. I echo do IRQ, and you could do this. This is kind of a cool thing you do. Echo do IRQ, cap is case sensitive. So do underscore caps IRQ and pipe that or redirect that into set ftrace filter. Everyone got that? Cool. Now echo function underscore graph into current tracer. And after you do that, cat trace. This shows you the interrupt times, how the latency of all the interrupts that are happening within your system. And it's pretty accurate. Like I said, the function graph tracer is still in the nanoseconds. So you can see some big whoppers. I mean, I've done this once, and I found like something that took over a millisecond. I went, what the heck was that? Ended up being the Wi-Fi card. Let's see. It's great, but it doesn't show much data. both the function and function graph tracer shows you functions. It gives you very much a lot of information, gives you timestamps, but I don't see variables. I don't see parameters. I don't see things that are also a little bit more interesting of looking at the code, what's happening within the kernel. So what comes about is what we have is called trace events. Trace events are built on top of something called trace points, which are positions within the kernel, and there's like over 1,000 trace points within your kernel that allows you access to specific variables and data within the kernel. They're grouped by system. There's a lot of them. The ones that I'm mostly concerned about. So you'll see sched, IRQ, net, syscalls, module, KVM, exceptions, C groups, and many, many more. It's like, but wait, there's more. OK, do this. LS events. Those are all the systems of trace events within your kernel that's running on your machine right now. The trace events, the actual trace event is grouped within those systems. So for example, the sched group, you'll see sched switch, sched waking, and a bunch of other things. Process fork, that's actually when a process actually forks. The exit, process exit, exec, pretty self-explanatory. When a task migrates from one CPU to another CPU, when it changes priority, we have things. So if you do, let's do this, ls events / sched. These are all the scheduling events that you have. You'll also notice right there, I just highlighted it, but I'll point to it here. The enable file, that's how you enable trace events. Like I said, here we go. Echo no op to current tracer, turn off your function graph tracer and everything else. You might want to echo 1 to tracing on in case you've turned it off and you forgot about it. But let's echo 1 to events / sched waking / enable. Use your bash completion, please. Tab, tab. And do it for sched switch as well. And after that, cat trace. Yes?
For this tracing, if you turn it on, does it have any properties with eBPF?
Does it interact with the eBPF?
Yeah.
OK, that's a whole nother talk. But this came way before eBPF, and eBPF has hooks onto trace events. Yes, this is actually how this is how eBPF.
But if you close open, and
oh no, it won't affect eBPF. eBPF actually, the tracing, the way I wrote the trace event system is very much a abstract module system. Anyone can plug and play and use it. It's a subsystem. The tracing is a subsystem, so you can have multiple people using it. It just basically tags. It makes a loop and just. And right now I'm actually working on that. There's only one attached to it. It just jumps straight to there using some magic. Modify the code. Like I said, the security folks hate me. I do everything that root kits do. Yes. So enabling trace events. So here, inside this whole mess of stuff, you'll see, I notice here, it's not the best, like I said, contrast. Contrast isn't that bad. Here's the COM for send controller. I have no idea what this thing was, but I just said, here's where it woke up. Here's where it was scheduled in. Fun. That's just a lot of data. By the way, if you want to enable a full system, a group of these events, I can say, screw it, I want to enable all sched events. Just echo 1 into the enable file and try it in events / sched / enable cat trace, and you'll see everything. A lot of data. And if you want to enable everything, just echo 1 to / enable events / enable. By the way, you could do it the other way around. You could enable everything and then go through echo zeros into things you want to shut down. So basically echoing 1, echoing 0, and if you cat the enable, it'll tell you the state. And it's funny because if the events, like a lower graph, say if you echoed 0 to events enable, then enabled sched events or any sched event, and then just cat the events enabled, it will show a big capital X, meaning that something is enabled but not everything. So what's in the event? Now you can actually see the event, and this is information that we'll be using later on, which will be, so if you cat events, sched switch / format, take a look at that. You'll see this wonderful design. The first part of this design, of the output, okay, the first thing obviously is the name. a ID, which is what's used in the ring buffer, and the format. The field, the first part with before the space, this is the general, all trace events have this exact same common events. You'll get the first one would be the common type. The common type is basically just saying, what type of event am I? What will be there will be that ID. So inside the common type will be 312 on this event. What's the flags? The flags are basically whether interrupts were enabled or disabled. Preemption will tell you if preemption was enabled or disabled. There's also more information in there like which context we're in. Are we in interrupt context? Are we in NMI context or whatever? After that, and the process ID. After that, you'll see that we'll have the previous com, and this is the specific data for that specific event. And underneath that, it shows how do you make sense of all this. Yes?
Why is it signed?
What is that?
Why is it signed?
Because it must be signed in, the type must be a signed variable. Whether or not it's actually that's a good. The question is why is the PID signed? Up here, you'll notice up in the common PID, and even down below it, it says PID. It says PID signed, and the way it does it actually does a little, is one. It has that little trick. I can't remember the exact thing. Like is 0 greater less than 1, or is this type of 0? It does that thing to determine whether that's a 1 or a 0. So that's actually automatically done by the compiler. So the compiler said this is a signed variable. So why it's signed? Because the kernel made it that way. And then this horrible thing that you see is how to print it. I made it a little prettier for your viewing pleasure. And this is what it looks like. You'll see the previous comment. If you look at this is the actual data that comes out. This is actually the code that is run, executed in the kernel. This is actually the printf to display. It reads the buffer, parses it like you saw there, and then it actually throws it in. That rec is the structure based on the way the information was done, and this is how it prints it out. The funny part is this looks really, really ugly, but it's because user space doesn't know macros or doesn't know enums. It doesn't know things like that. So before it goes to user space, because tools need to parse this, but you don't know how to parse like this. Because no one knows what task stop is. It needs to know what a number is. So believe it or not, basically this output is here. Everyone compile with -E, GCC -E. Yep, a few people. It basically runs the preprocessor code, so you get to see the output of the preprocessor code before it gets into the actual compiler. So all your macros are expanded. That's all we did. We just expanded all the macros and all the enums and everything. That's why it looks so ugly. It's just because it's expanded, because tools need to know what it is. It doesn't know what, this is for humans. So if you actually went into the kernel code, this is what you would see. TMI. Too much information could be worse than not enough information sometimes. You have all this signal or noise, or the signal to noise ratio is really bad. So we want to just see specific things. So that's why there's a tracing file called filter. So another thing you use for human people is to read your format. We don't care about the printf. We just want to see what variables are there. And now I could do something like, OK, everybody, here, let's try this. It's kind of a long command, just to give you an idea. Echo, quote, prev, prev underscore comm, space, equal, space, quote, bash, if you're running bash. I'm assuming everyone's running bash. If not, whatever shell you're running. Quote, space, 2 ampersands, previous state, single ampersand, 0x02, quote, greater than, and do the old events, sked, sked switch filter. Use your bash tab completion. Actually, I should make this, I should add a completion so that it will actually fill out the other part too. It actually would be able to do that with the completion things. I'm sure I could write code to do that. And then what?
Just touch the files in that directory.
Yeah. Well, no, it's not just, well, no, I'm saying for the command, the prevcom, it'd have to parse the format file. Yeah, so I'm saying you could write a bash completion script that you could be, if it knows that you're in the tracefs directory, it will actually know, it'll fill it for you. But then you need the quote, which then kills it, so I don't know. But actually, later on, I could do that when we come up to the second part of the talk. So everyone try that? Hit echo 1, boom. When you cat your trace, oh, by the way, I did echo greater than trace. That clears the buffer. If you just write into the trace file with a greater than sign, it clears the buffer for you. So cat trace, and you'll notice that you're only tracing your schedule, or when your task runs in the D state. The D state means it's blocked on something. So that 02 is, I want to be blocked, the D state. You have to kind of figure that out by looking at the code and that crazy thing. Everyone try it? Can I go to the next screen? Anyone?
No.
No? OK.
One question about the app step. So how the app step becomes computed, whether you are able to use RDT for x86, whether you can use on the user level, whether you can use RDTSC, read app step, and then current.
The timestamp is defined by the, I don't think I talk about it here, but if you see in that directory, on the top level directory, you see trace_clock. And that tells you what timestamp you use. You'll see local, global, x86 TSC, raw. There's even, I think there's even a counter. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for each event. Right now, it uses the sched clock, which basically is what the scheduler uses. And the timestamp is basically the uptime, that's in seconds. And it's the uptime, and the actual resolution's down. It doesn't show it. It only shows microseconds, but the resolution of the timestamp is nanoseconds.
You're going to be correlated with dmessage.
No, it will not be. It will not, because dmessage doesn't use the sched clock. It uses a different clock. There is a boot clock. I think one of the clocks is the, like I said, you can switch which clock you want to use. And one of the clocks is the same type of clock as like the print K clock, I believe. Everyone ready? Yeah. OK. So that's what you get just to show you how you can filter something. That's why I wanted to just get you there. But then let's do something even more special. Let's do event triggers. So what does a trigger do? A trigger is actually, let's put action onto it without even using ePPF. But you can actually make an action happen on your trace event. So you could turn on tracing, turn off tracing, make a snapshot. What a snapshot is basically, there's a second buffer. You'll see a snapshot file in your directory. That's a trace file. That's basically a snapshot. It's basically when you enable snapshot, and actually you could enable, that's out of the scope of this tutorial, but you could actually automatically do it snapshot at any time, which basically makes the two buffers swap. So one is always static, and the other one's always being written. But once you hit the snapshot, it swaps the two. The other one becomes writable, and the other one's static. So then if you just want to constantly look at things like, give me a snapshot, boom. And you can actually have an event happen to trigger it, a snapshot. You can do a stack dump. So if you want to see where something is, you can see how you got to that event. You could enable another event. You could disable another event. Those last two I'm not going to talk to. You get a little bit complex. So say we don't care about this or the state. You see, you got, OK, up arrow. Since everyone wrote that command, go back up arrow and do your previous command. Make that, or if you still have it, don't do anything. I want you to have that filter enable. But let's make a trigger with that filter as well. So whenever that happens, when you ever schedule, kind of you could do a cut and paste from, because you're going to need that same filter or that same action. I want you to echo stack trace, all one word, space if space that exact same command you just wrote, and pipe that into events sched switch trigger. So if you're good with bash and you know how to up arrow, this should be quick. Now triggers are not affected by tracing on, or is not affected by tracing on or whatever the event being enabled. If you enable a trigger, this will have the trigger triggers. So you actually need both. If you want the event to show up and the trigger, you have to enable both. So they are not related to each other. So the event will happen, then the trigger will happen. And what you should see here is what? What's that?
Okay, invalid argument in the echo didn't like the stack trace.
Did you do it just like this? Echo, let me take a quick look. Can I see what you did? OK, echo stack trace if com equals bash and previous, and that was the exact, boom, greater than events, right error, invalid argument. Oh, you've left M out, 2 M's.
2 M's. Oh,
yes. I'm almost at a point. Good. Hopefully, I'm hoping I should see how many. Yeah. So everyone got that?
Some of these features specific to the version of the kernel. Trigger file then.
You don't have, well, okay, how old is your kernel?
CentOS.
What?
CentOS 7.4.
And what's, if you do a uname dash R?
Yeah, 3.10.
Ah, yes. that's like 5 years old. So some of these features have been written. Sorry, I should have said. I said a recent distro. Someone else had any question, or was that?
Is there an easy way to reset all the filters and enable that?
For the filters, you just echo 0 or echo right into that thing. You also do it higher. I'll get to that too after the break. So I might screw up your computer, so you have to come back. And you should see this. I'm going to move on because we want to do a break, and I still got more to go. How to disable it? For the trigger. The trigger's special. I know it's OK. We're a little inconsistent, but us kernel developers are sucky at API designs. So echo, have to put the quote. Make sure you have the quote. You don't want that. You don't want to put an exclamation point in bash shell without quoting it. So echo bang. Period, bang, stack trace, bang. You don't have to put the whole filter. Just put the stack trace and into the event schedule switch trigger, and that turns it off. So I'm almost ready for the break. Wait, did you need this? Yeah, just to the trigger that you just write to the wherever you wrote to the file to the trigger. Just write the whatever, just cat trigger there and look at it, and you'll see it in there. By the way, if you have the source code downloaded and of the Linux kernel, the Linux kernel, if you go into tools/testing/self-tests/ftrace, it's a long thing. You can remember that. It's there. Search for ftrace in the tools. You'll find it. There's a ftrace test that runs all these tests. But if you look at it's all bash scripts. And it basically shows you, it enables and disables this. So if you forget something and you can't understand the documentation, you want to actually see an example. The example is in the ftrace tests code. Run it. Because then if you find a bug, please report it. So, okay, go on. Everyone got there. So, ftrace is a tool with anyone that has busybox. So embedded people love me. You don't need a tool. You don't need a compiler. You don't need anything but a way to write standard input, standard output into a file and read a file from the standard input output. It's extremely simple. It's the quickest way. That's why the first time I rooted my phone, I was playing with ftrace like crazy because all I needed was a terminal, had echo and cat, and it worked. I'm not allowed to root my phone anymore because it's got work on it, and they don't let me do that. So. But it can be very tedious. A lot of things to remember. It's not very intuitive. It takes a lot of painstaking stuff to redo this. So this is where it's good to have a break. And after this, I'm talking about the tools that makes all this. Basically, this was just to teach you about ftrace. After this, it's going to be a way of making it much easier to do the exact. But this is hopefully could get you motivated to come back. OK, so 10-minute break. Be right back. Thank you. Yes, thank you. What? So, obviously, using echo and cat and all that is awesome because it's so simple, but it also sucks because it's so simple. So, a long time ago, I created this tool with an awful name called trace-cmd. There's history behind that name, and I would love to change it, but it's too late. Everyone says they use it they have it in tools and scripts, so I'm sort of stuck with it. It interacts with the tracefs file system. In fact, actually, if you were to unmount the tracefs file system right now, switch to root, and run, trace command show, it would actually mount your file. You have to do it as root. It would actually mount your tracefs file system for you and do that. So everything I just told you about, you can forget now. But it's good to know. Basically, everything I did in the first half of this talk was basically how trace command interacts with ftrace. But now you can forget about the tracefs file system. You only need to worry about the tool. So it uses another file. If you were in that trace-fs file system, it uses a per CPU directory because the buffers of ftrace are all per CPU for efficiency. And it will actually, you'll see a trace pipe raw. That's how it reads the data directly from the ring buffer. And it's just raw binary data, which is why you need that, that format file that explains how to parse the binary data and how to present the binary data, that horrible print format thing that is almost human unreadable, but very tool readable. It uses the Splice 2 system call. How many people know the Splice 2 system call? Okay, sort of. Splice 2 system call. Okay, how many people are C programmers here? Yep. Okay. Splice, I have to tell you everything about the Splice system call. It's an awesome system call. It works with pipes. But say if you have copy. You want to copy a file from one file system to another file system. And the way you would do it is you would do a copy open FD. The naive way of doing it would be you would open up a file descriptor on for the file you want to copy, open up the right file descriptor for where you want to put it, read from the one, write. Well, what's happening? You're taking data from the kernel, copying it up to user space, and then copying it back to the kernel. Very, very slow and basically wasteful. What you could do is instead is create a FIFO, or a pipe, sorry, not FIFO, a pipe, for input and output, and attach the file descriptor of the input file to a pipe, then create another pipe where you connect the two pipes. And the second pipe writes to the second file. And the way you talk to the pipe is you use the Splice system call. And what you're telling is, tell the kernel, hey, I want the data to go from this guy to that guy. And since you're in page cache and everything, and the data is already in the page cache, so basically it copies from the disk into page cache, and then takes that same page cache and writes to the new file. Never going to user space. Much, much faster. You could try it, write your own copy version, and use Splice and see how, and do like copy gigabytes, and you'll see the difference tremendously. Yes?
Don't do that.
Why?
Not handle errors.
Was it?
Not going to handle errors.
It works.
IO error. We changed the 5%.
Well, yeah. Okay, well, then you figure it out. I mean, but basically, this is what trace command uses to write from the ring buffer into the file. It just uses Splice and just whips it in zero copy from the, so it tries to keep as fast as it can, keep up with everything. So, like I said, forget everything you learned so far. Now cd to a directory that's not in the sudo directory, because you're going to start writing to disk. And if you try to run trace command from debug.fs or trace-fs file system, you'll get an error because it will say you can't write to this file system, even if you're root. And I already believe everyone installed everything. Oh, there's a make install doc. By the way, I was very adamant to make man pages. So if you did the make install doc, you could do man trace command, which gives you all the lists. Then you could do like trace man trace command list, man trace command record. All that is in there. And I have bash completion as part of it as well. So if you did the make install, trace command has bash completion for most of it's. I was supposed to do more. I forgot. The speaker's dinner went for too long. I was going to write a better bash completion, but it still pretty works. So let's go back to what we did before. And let's try to figure out the one little thing here, which just, okay, here it's going to be a little bit typing. So trace-cmd space start space -e, which means event, sched switch, -f for filter. The same thing you wrote before, quote, previous com 2ems equals, quote, bash, the exact same thing, end quote. Continue the line, same line, don't, I mean, whatever, I put the little slash there just in case, so I only had so much room on my slide. Dash capital R, which stands for trigger, and it's one of these things, trace command is going, the start and record has got option bloat, so I'm running out of letters to use, so some of them I don't like doing long, I do have long commands that represent it, but I still like to do short commands. And then the same thing, stat trace, blah, 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 blah. Hit enter, trace command show, and you get the exact same data. Yes? Ah, you're right. That was a cut and paste error. You know what, actually it's funny because I did that and I got the error and I fixed it, but when I did the cut and paste, I used the broken version. Because I did a lot of cut and paste here and getting things here. So basically I did all this on my laptop just a couple weeks ago. Everyone got that?
No.
No, come on, you can just up arrow to what you already wrote before and just cut and paste. What, you got no output? Oh, wait, you got no output from the previous one. Or are you writing bash? Oh, okay, if you have to see me, you should have saw me through the break. I would have liked to. So if anyone's having any errors, see me afterwards and we'll work on it. I want to make sure you guys actually everything works. And this is great because if it's not working for you, I'll take it back. Yes?
For me, that particular event filter, it does occur, but it takes quite a while to hit it.
Hit event?
Yep.
Oh, you know what? Because I'm actually, the funny part is, I'm triggering off of when your task is blocked. So maybe you have to do something. So you just say enter. If your system's not doing anything, maybe it's never hitting the blocked event. So the event never actually occurs. Maybe I should just have you guys remove the previous state and you'll get to see everything. Or maybe make previous state equal 0. That's how you could switch it. Instead of doing previous state and 0, 2, make it previous state equal 0. Try that. See if that does it. So for both sides. So it's.
I've got output eventually anyway.
Oh, see, yep. You actually, for those that didn't event, that's because I probably should have said this is the block state. If your system's never blocked, you won't get any output. So maybe that wasn't a good example. Okay, here's something that is very useful, and it's not fully developed, but it's getting there, and it will be there more. So please keep updating your system. Do trace command stat. This shows you everything you forgot to reset. Now do trace command reset and then trace command stat. So this cleans up all the dirty crap so those that didn't come here that have all that stuff on their system still running, slowing their systems down, they don't have trace command reset. Unless they're watching the live feed, damn you. Okay. By the way, trace command reset does something that if you ever do trace command reset and then you jump into the file and then you start doing stuff and you're like, why am I not getting output? Trace command reset did something I kind of regret doing, but I'm afraid to not do it because I'm like Linus Torvalds, don't break backward compatibility. I very much have strong rules with no breaking backward compatibility, so I don't change things very easily. If it did it one way, it kind of always does it that way, even if I hate the way it does it. Trace command reset will, if you do trace command stat, you'll notice, there we go, tracing is disabled. So that means tracing on file has 0 in it. So a workaround, if you do trace command start, because trace command start resets everything before it does something, and then I say start the no-op tracer. If you remember what that is, do nothing. You'll notice that tracing is enabled. So basically what start being no-op is just a hack that basically uses the fact that the start resets everything, and then I start nothing. So record and start. So start enables tracing just like you did. It does the cat show. You get to see basically everything that we did up to date. Record is something new. Record is saying, I don't want you just to start something. I want you to save it. So this way I want to record gigabytes of data. And you can do that really, really quick, like basically in half a second with the function tracer. So start is compared with show. Record is with report. They use basically almost all the same commands. So start and record are almost identical for almost every single command. E is for events, P is for tracers. When I first wrote trace command, we used to call the tracers plugins. So I used -p. I wish I would use -t, but I'm sorry. Like I said, I don't break backward compatibility because of -p. We have plugins that has another meaning now, but historically, we're stuck. So now the title of after the break and everything, now I'm getting to what the title of this tutorial is about. Let's see what the computer's doing. Let's write ourselves a bash script. Everyone, okay, open up your favorite editor. Vim, Emacs, Nano, Joe, Q, and echo. And let's just write this. Hashtag bang /bin /bash. Make sure that's all together, tight, no spaces. You can put a space, I don't care what you do, just hit new line, multi-new lines, whatever, and just echo, quote, hello world, bang, quote. Everyone got that? Do I need that? Everyone got it? Good. So, I talked about Strace. Let's run Strace. Everyone should have Strace installed. If you don't, you should install it someday. And if not, just watch what everyone else is doing. So when we do strace hello, and you do ampersand greater than, everyone knows about ampersand greater than? Or yeah, bless it, or yeah, greater than. That just basically redirects all standard input and output to one file, so you don't have to do the magic stuff. That's a bash enhancement. And then cat out, and or vim out, or Emacs out, Joe out, nano out. And what you'll see here is the exec-v, where execs hello. Loads a bunch of libraries. It mmaps stuff, a lot of more mmap calls. Accesses more libraries. Reads this elf file. Where the hell did that elf file come from? More libraries. Wait, yeah, I didn't make an elf file. More libraries, more library, or more mapping. Continuing on, it open at, now it's like opening this hello thing. I'm like, wait a minute, why is it opening a hello now? And does a whole bunch of other stuff, reads, writes. Here's our hello world. Boom, there. So here's, we look at open app, and the read, you see our file there on strace, so it's reading our hello, it reads the bash char there, and x hello. So this is basically our bash stuff going on right here, but weird. What's all this other funky stuff that's going on? So how do bash scripts actually work on Linux? I'm sure several people already know the answer, but let's do a deep dive into the actual kernel. So let's have a look at exec-v, which is how you exec. Basically, it's a way of changing the world of a program from one thing to another thing. So first thing I do is I want to find the exec-v system call within the kernel. Now the kernel could call it anything. It could call it Bob, the function. But luckily, the system calls are sort of mapped. So let's do this. Trace command dash list trace command list dash f, which means function, exec-v, and see what you get, because you'll get different things depending on which kernel you have, because they've changed this throughout the times. I don't know what you got. So search for that sys what? You get nothing. So trace command list dash f. Right, some of them you'll get capital S, little y, capital S. Yes, this is new. That's why yes. What kernel am I running is the latest Debian testing kernel. I did a apt-get, I did an aptitude update.
I think you were using 4.8.
What?
4.1. You were using 4.8. You should have it first.
Oh, okay, yeah. Okay, I had it up there. 4.18. So that's the Debian testing kernel. Like I said, I want to do this on a distro kernel. So and I run Debian testing on my laptop, and that's what I did it on. So, but I know CentOS, was the CentOS guy going to leave, or is he still here? Yep, there he is. Yep. CentOS is probably, I don't know what you got on that one. But that's why I told people to do this. Oops, did I go back? I just want to make sure. Yep. So again, for more information, man trace command list, if you want to see what that does. But we don't have details for that. We just know that we found exec-v. So let's cheat. Okay, actually, you may not have to. You actually have, this is case sensitive. Be careful. Actually, it may not be, I don't know. Trace command record -p function _graph -g. quote, star, the prefix you had, capital S, little y, capital L, whatever that prefix was, underscore exec, just exec if you want, star, quote, and your hello script that I hope you made executable. Because if it says command not found or something like that, you forgot to put change mod plus x, hello. Everyone got that? Everyone did that? Was it? All right. OK. Any problems? Let me know. Everyone got it? Everyone ready? Anyone not ready? Did you change mod or invalid object? Oh, wait, what kernel do you have? And you got an invalid object for, you got the trace-cmd record -p function underscore graph. Did you have a function graph tracer enabled? Yep, -g space dash quote star. If it doesn't, it'll be an invalid argument if you don't put in the right. Yeah, case sensitive on the. Yes, it's case sensitive. If you don't put the right function name, you'll get invalid argument. Was that? What did you type a -g? It looks like you might put -f. OK, we're ready. Let's go. And then trace command report. So now you'll see the actual function of your, you'll see your events. You'll see the function that started and only that function. The -g means graph that function only. And you can put more than one function in there. So it doesn't trace anything else, it only traces, but there's a limit of how many functions you could trace or do that to. But it will let you only trace that function. So maybe I'm only interested in one thing. So I look at here, and yes, it's pretty big. A lot of info there. And my function is 16,870 function calls for hello world on sysexec. Not even hello world, just sysexec. A lot of info there. But interrupts also happen. So if you do trace command report -I, remember I told you it tells you what context you're in? It will then remove interrupts, because while it's recording, interrupts are happening like crazy on your machine. Every time you're even typing or whatever that, or timer interrupts or whatever, it's going to you only record that, because even though it graphs that function, if an interrupt happens while it's graphing it, it records the interrupt and then goes back down. So -I tells the trace, since the data is already on a trace.dat file that we could actually analyze, we could tell the report, I don't care about interrupts. Or soft interrupts. There's two types of interrupts. There's a hard interrupt and there's a soft interrupt. So if you do the trace command report -IS, pipe that to wc-l to see how many events, it should bring it down quite a bit. Everyone okay with that? So let's do trace command record function graph. What was that?
Still more than 6,000 with IS.
Oh, it's no there. Yeah. Well, mine was over 10,000. Yeah. Add this. Unfortunately, this is a long command, but I think it might. Bash completion might work if it was installed properly. So it might work. I don't know if you do --max-graph, maybe that'll fill it out. I don't know if bash completion works or not. It would be my first test case. It worked. Put 5, and then run it again. Run the record again. By the way, a feature in this will be, I shouldn't be having to write in the record again. The report should be able to do this itself, but I haven't implemented that yet. So that's on the to-do list. If you run it again, it drops down by a hell of a lot. What that means is only go 5 levels deep, because I don't care about all the other crap. I just want to see let's see what it's doing at 5 levels deep. So 347 events is not bad. Shoot, I lost a output. Well, anyway, yeah, because I think it might have been in the very beginning. Yeah, you'll see that a lot of these things, what you'll notice is if you look at your call, you might see something like condition resched is also kind of busy. I don't care about condition rescheds. That's called like all over the place. So if you want to remove something, if you put -n, which means no trace, which is basically the no trace file, you could tell it don't trace condition resched either. So if you do this whole thing, by the way, some Kernels might not support it because it uses no graph trace. Doesn't really use a no trace, it uses a no graph trace. So it might not work on some older kernels. -n, you could make it even smaller. So I lost another 100 functions. And let's just do 4. Let's just do it to 4. Then do it to the left. So basically, this is, you don't have to do it. I'm going to show you what I did. So I did a report-is. And I'm just looking at these functions. I'm like, OK, we have the exec. It gets the name, calls the file. An interrupt happened. But you know what the funny part is? The reason why, SMP IRQ work interrupt, this function gets called because I was tracing graph the functions. It gets called, but before the interrupt, the kernel could set the context. So the inside this, it's inside the IRQ enters where the context gets set. So actually, you'll still see interrupts happen. But the context for it is not recorded in the buffer until the kernel says the context is switched. So we're actually there's a little race window there that we're recording events when an interrupt happened, like from when the interrupt actually happens to where the context kernel says we're in interrupt context. Well, we get the functions that are called between those 2 points. That's why you'll see that. You'll see these in there. So user share files, stuff like that. That's the interrupt. Let's see here. You got a bunch of open execs, get, switch, malloc. And keep down, copy string. Fun stuff. Here we go. You get the search binary handler thing. And then down here, you'll see load script. This is where it's doing something about loading a script. That sounds like what Bash would do. You get there? Yeah, it did a lot of work, didn't it? It's amazing. So let's see here. What is this load script doing? Let's do the record again. But instead, I just want to graph load script. Max def 3 if you want. I don't know. Doesn't matter. And non-scale, you could record that. So basically, just up arrow, delete everything. Just let's see what the load script is doing. And hopefully, your kernels have load script on it. Everyone's got set? Go. So I look at load script, and you get all this lovely stuff. Fput, it's just basically putting a file descriptor away, whatever. Copy some strings, more things. Does a search by thing. And here's something very interesting I noticed. It calls load script again. Load script calls load script. Now, you realize inside the kernel that it has a fixed stack. I saw this and went, wait a minute. That's recursive call. We don't do recursive calls in the kernel because recursive calls can easily blow away a stack easily and cause very bad things. I'm like, oh my God, this is like Bash. It's calling load script. Let me look at what it's doing. I'm like, what? You know, is this a bug? Can we exploit it? So I looked in the source code. If you have the source code available, you could look at it. You could do a search for load script. I believe it's like, I forgot which file it's in. But anyway, you can look at it. And I said, hey, look what it's doing right here. Inside load script, it searches for, it checks the, I believe this is called the binary parameters. That's what the BPRM. I'm like, that's one of the worst acronyms ever to have. I'm like, you see this BPRM all over the place in the kernel exec code. And I'm like, what the heck is it? It's binary something. What is PPRM? I found binary parameters. Anyway, the buffer, that's the file that basically that it's mapped. It's the beginning of the file. And it checks the beginning of the file that you're about to execute. You say, I want to execute this file. It reads the file, looks at the first couple characters, and say, hey, you got a pound negative sign here. You know, if it's not that exact. But so we're loading a script here. And then it calls later on down here, search binary handler. So I'm like, can I repeat this? You could try this now. This is going to be fun. Create a file called, you know, bang pound / temp / blah, and type that in and put that into the file called /temp / blah. So in other words, I'm telling the loader to load itself again, which means it will load itself again and load itself again. I'm like, I'm going to crash my system. Are you nervous? Change mod X and run it. Let's see who's brave. Got it? Nope. Did everyone get this error? Too many levels of symbolic links. It's not even a symbolic link. It's screwed. That's a bug. Incorrect error. Actually, it's probably whatever the incorrect thing. Bad interpreter. That's true. Bad interpreter. So, what happened? Let's record it. So, let's look at loads. Let's graph load script and on blah. So I go there, and this is what I see. Trace command report dash capital O. You could do. You should be able to do your bash completions to see what dash capital O is like. Basically, some of the events interpreters. There's like plugins, real plugins, which means how do you read this event? So you can load a plugin to say how to read in a particular event. So the function graph tracer is a plugin, and the plugin has options. And one of the options is tail print, which means I want you to not just give me a squiggly on the exit. I want you to tell me what the function name of that function was called. So I get the, if I can get this, I get these load scripts comments at the end of the functions. Without that, without tail print, this will just be a bunch of little squigglies. So if you want to see what the function is, I want to see it. So this is what you see. And that's how many layers. Let's say one called one. Well, maybe this is the same level. So 1, 2, 3, 4, 5, 6. 6 layers. It kind of died there. So let's, OK, grep-c2. I'm going to give a little more information to see what's going on here. And it does a lot of work here. And down here, you'll see it does something different. The first one does search binary handler. I'm like, wait, what's this thing doing? So I go there, and look at this. Recursion depth greater than 5. There is a check to make sure that it doesn't kill itself. So this is interesting. Let's see, just the events, please. I don't even know what I'm talking about. Let's see the world. So if you want to trace everything, that's right. This is about function tracing. Let's see events. So let's see all events. So if you do trace command -e all, it will in sleep 10. You get this. Everyone got that? Do trace command, record -e all. This is the command. What? I'll keep it up. OK, trace command record. Come on, I type as fast as I talk. So everyone got it? No. OK, trace command. RE, tab completion should work. Yes?
Does the trace record, skip records, all the, let's push all the buffer effectively?
Wait, was it?
That's if you keep recording, like that it push all the, that's guaranteed that push all the buffer.
If you just type record without the sleep 10, just without putting that sleep 10, just let it go. It'll say hit Control C when you're done, and it'll just keep going until you fill up all your disk space. Yes, it just keeps. It tries to keep up. It's a producer consumer.
So if it cannot keep up,
you lose events. Yep, and you'll see inside the thing event lost. Yes, it'll tell you. And sometimes because since I'm very much backward compatibility, I can't change the way it did, and I wanted to add more information about it. If there's space in the end of the buffer, because it's broken up by pages, and there's space to put in, like if there's 4 byte space, it tells you how many events was missing. Otherwise, it just has a flag that says events were missing. It'll just say dropped events, which means there wasn't room to put how many. But if it has room, it'll tell you how many events were dropped. But you will always know that events were dropped. So you get this, right? Really informative. If you're a computer, how about this? The contrast may not be the best, but hey. Welcome to kernel-shark 1.0. Well, it's prettier. Kernel-shark was created in 2009. The GTK version, I created it because I had a month to play around with something, and I was a GTK programmer before I became a kernel programmer, way back in the mid-90s. And I'm like, I'm going to brush off my GTK. I haven't done it in a decade. So I relearned GTK and wrote this thing. But then I started going back to work on it, and kernel-shark became my idle task. So I only worked on it when I had nothing else to work on. And then one day someone said, you know, I haven't seen a commit in 2 years. Well, I'll show you how busy I was. Again, talking about working for VMware, Dirk Hondo, who's here, who's the vice president here, he told me, Steve, is there anything you want, in the open source world to work on? I'm like, I need kernel-shark's work on. So this developer named Jordan, I'm not going to pronounce his last name because I always mispronounce it, from Sofia, Bulgaria, was hired. And he's done a fantastic job. He liked Qt, and I told him, you know what? I've been wanting to rewrite kernel-shark for the longest time because I did it, just kind of rushed it, and I'm like, okay, I found out that I did a lot of things I didn't like, so let's just throw away the code and write from scratch. So for a year, he's been working on it. So now, just this yesterday, I finally deleted the GTK version, and now we only have the Qt version. And it was written from scratch from Qt by Jordan. I've been mentoring him. He's been doing a fantastic job. So actually, I've introduced 0.9, it should be 9.8, actually. I'm afraid to do 9.9. Congratulations, you are all my beta testers. Bugzilla.kernel.org. Please play with this. Report any bugs you find. Yeah, someone already got a core dump? Awesome. I was originally going to say, let's call it 1.0, but Jordan's like, wait, no, only you and I have been playing with it. You know someone else is going to break it. I'm like, okay, captive audience. If you go to bugzilla.kernel.org, you see tools, utilities, you click on that, you'll see trace command, you can report bugs. There's a linux-trace-develop. Wait, someone sent me an email about a bug about compiling on Slackware. Are they here? Duncan, I think, Duncan? Yeah. Yep. Oh, it was you. Okay. Yeah, so you had issues. Yes, I got your email. I didn't get a chance to reply. Yes, thank you. Yep. Yeah, but you got past that. But I was like, well, that's right, you're using Slackware, right? Yeah. Wow, that's why I started on, but hey. Anyway, 1.0 is kind of coming out. I'm going to call it 1.0 because that's what my slides were originally. Everyone, so do trace command record. What do we do? All record, you did that thing, right? Just write kernel-shark. Did you get something like this? Awesome. Whoa. Well, hopefully you don't have the. Wow, that's not much information. Well, did you do the trace command all?
Which?
The trace command record all. Oh, yes. Make sure you do a trace command record -e space all. I'll go back to, let's see, that one. What?
Does the GUI work remotely connected?
We don't have anything for remotely yet. I mean, you could do it over X windows. I mean, I've pulled it. I usually SSH to a machine and have it pop up, but I just use it like the SSH tunneling. Oh, okay. Yeah, you might. We don't have that working yet. That will come. There are. Well, this will come. This is where I wanted you here. Okay. Well, you know what? Afterwards, we'll work on it. If you don't get it, just watch and we'll work on it afterwards. Where did I do it? Oh, this right here on the top. You'll notice that I said tasks. So if here you hit plots, tasks, and you'll get this window. At the time, for some reason, I had a bunch of MySQL daemons running. So I just pressed and hold, press the left mouse button, hold, select them all. You have to hit enter. This is one of the things that there's a little difference between the two, but I guess it's a cute thing. I don't know, but the quiet because I always select them and then hit apply, and nothing happens. And I'll go by and like, oh, I forgot to hit enter. Because you can select them, but it doesn't actually select them. So when they're highlighted, they're not selected. Only if they have the checkbox are they actually selected. So you have to highlight, hit enter, selects everything you highlight. Or if you just click the checkbox, that works too. And then you hit enter and you get, well, whoops. Oh, wait, yeah, that's how you do it. But anyway, since we have less than 10 minutes, I have to go ahead. And let's do Java. How many people are a Java programmer? I feel sorry for you. I'm not. I was just pretending. This is like the first Java program I wrote in probably 2 decades. Everyone type this. What was that? No. I don't want to be a Java programmer. Just copy it from someone else then and say you didn't program it. Public space class place capital hello, capital world, open bracket, public space static space void space main, paren, capital S for string, left bracket, right bracket, args, end paren, squiggly bracket. This is why I hate Java. Capital S system dot out dot println, and this is kind of like why I'm not a big Python fan. I tell people I'm afraid of snakes. I like oysters. See how many people got that one. Colon hello world. Colon. Everyone got this yet? I should have put a prerequisite. You had to take typing 101 before you came here. I'm telling you everyone's got it or not. No, no, no. Anyone else not ready? Hopefully you have Java installed, because if you have Java installed, you just wasted all that time. It wasn't a prerequisite because I was afraid. I wanted people to show up for my talk. No one's got it? Or could someone just show them his screen so I could go on? Yeah, I got 5 minutes. See, you just put up the 5-minute sign. That's why I'm like, gotta go. We're almost done. OK. Did you get it? Well, actually, I should have put it on my USB disk and just said, here, open the file. I could have just given the file. I didn't even think about doing that. Actually, I probably could throw that in. I'm going to have to go. I'm sorry. Give me a couple more seconds. Because it's not a big deal. It's if you do it. Because I'll do it with you afterwards. I got to help you anyway. I'm trying to be nice. Got it? OK, I'm going to jump ahead. OK, now, when you got that, good. Now go wherever you saved that file. Remember where you saved that file, because you'll need the full path name for it, I believe. If you go up into Tools, go down and hit Record. Oh, yeah, don't worry about it. So hit Record. By the way, you could have been non-root, by the way, now. You don't have to be root anymore. In fact, actually, don't be root, because if you're not root, it will now, kernel-shark will now ask you for the root password. You type in the root password, you hit enter, and actually we have a separate code to do the recording that's very thin line, so it's going to be better that we can vet it, so you're not running the GUI anymore. I mean, it's a small GUI. You're not running the full GUI. You're running a very small GUI as root. It's a separate, actually, it executes a separate application to do the execution with a special pipe between the two. So once you get that, you should get this file, which is separate from the actual application. So we try to secure it a little bit better. We're still working on it. We still have to vet it. It's still not totally secure. So, but this is so people can run as root. And you'll notice this is kind of, we're still working on it. It's going to be much more featureful soon. But since the old kernel-shark didn't have this done very well, we'll do this. So you come in here and you'll see you export you can do a bunch of things and then export your settings and it'll save it. Or you can import settings and it'll pull it back. So whatever you do, you don't have to do it twice. You can click all events and it'll select everything, which I think is the default. Or you could go unselect it. It'll unselect everything. And then you could kind of click in and out, picking events. But let's do all events. I want you.
How do we get this? Sorry, how do we get this screen to start with?
What get to this?
We just didn't type kernel-shark by itself. We just give some arguments.
No, you just type kernel-shark.
Oh, I don't get that.
Oh, you type kernel-shark and then you hit Tools, Record. And then it gives you this, and then it gives you this. And then you type in here, Java. Whoops. Let me go back. Here, this is where the output file will be. Right now, it's my home directory. Type Java space wherever the file, full path name to your file. Then hit Apply. Don't hit, just hit Apply. Because Apply will show you, will come up here and put everything, it will put the command, the trace command record up here. And then you could go and you click, it has a read-only thing. You click that to turn off the read-only. And then you can add in, let's do -F -c. This is because this is things that we're going to add later on to down here. But for now, we let you modify. You can put anything you want in here. This is actually a command that will be executed. So you can put any parameters. Capital F means follow this function. Only trace this function. Don't trace anything else. But it will trace wake-ups, which means it will trace events that woke it up. And -c means record all the children for that as well. Depending on certain kernel levels, it might have different ways it does it. It'll either use ptrace poorly, or newer kernels have kernel support for it, which will make it will definitely work very well. So upgrade your kernel. And once you let it go and hit captures, and we're about time, I got to get going. Go down here, now hit capture. Yep, 1 minute. Welcome to Hello World. This is just Hello World. Java. Core dump, you get that too. Which is a bug, which I said Bugzilla report, awesome. But anyway, this is the output of Hello World of Java. And this is everything you could do in here. Thank you. I don't think we have time for questions or anything, so.
We don't have time for questions, but feel free to.
Yes, yeah, I'll
get your lunch.
I'll stay after. Well, I'll go right out here. I'll hang out here. Help anyone that wants to do anything. Any other questions? Feel free. I'm going to stay out here for all of lunch or something like that. Or maybe I'll go get lunch or something and come back. But yeah, I'm here to help.
And a small token of appreciation
from
the conference organizers. Great talk, great tool.
Thank you. Thank you very much.